Welcome to a lecture on the physical dimensions of climate change, in which we will consider, first of all, a global picture of the climate system. We'll then look at how Earth's climate has been changing over the past century. We'll focus on how the climate system has changed and how carbon emissions, increases in atmospheric carbon dioxide, are the major driver of that change. And finally, we will talk about how we model the Earth's climate system and how we use models to look into the future. So a global picture of the climate system, perhaps the best way to look at the global climate system is through the flow of energy. Here is a diagram that shows incoming solar radiation to the Earth's climate system and outgoing long-wave radiation. It's the balance between these flows of energy, that is solar energy and long-wave energy, that to first degree determines the temperature of the planet. You can see on the left that the incoming solar radiation is composed of various parts. Most of the energy coming from the sun reaches the surface to warm the surface. That's the 161 watts per meter squared absorbed by the surface. There is, however, about 30% of that incoming radiation from the sun, which is reflected back to space, and it's not available to warm the Earth's climate system. It's reflected by both clouds and the surface. On the right-hand side, we have the outgoing long-wave radiation, that in the long term must balance the incoming energy for the Earth's climate system to be steady and stable. This outgoing long-wave radiation begins at the Earth's surface, where the warm Earth's surface radiates long-wave or infrared radiation upward. Some of that radiation is re-radiated back to the surface by greenhouse gases and clouds, and the rest escapes to space. You can also see these two arrows in the middle of the diagram, the thermal arrow and the latent heat arrow. Those represent two ways that the Earth's surface removes heat or energy from the surface and deposits it into the atmosphere, either through sensible heat, that's the small thermal term, or latent heat, which is the evaporative term. As I said, the climate system to first order is determined by the balance of these flows of energy. Anything that disrupts this flow of energy, in other words, if there were less solar radiation coming in, the planet would cool, or if there was a way to hold back the outgoing long-wave radiation, you would hold more energy into the climate system and therefore warm the planet. And that's exactly what the greenhouse effect is. If you increase greenhouse gases in the atmosphere, you're going to decrease the amount of long-wave radiation escaping to space, therefore putting the planet out of balance. And you can actually see in this diagram that small number at the bottom of the diagram, the net absorbed 0.9 watts per meter squared, is the imbalance that human activity has placed the climate system in. And it's that imbalance, the increase in greenhouse gases that lead to that imbalance, that causes the planet to warm. So how has the planet climate system been changing? Well, here is a figure of the anomaly or change in the Earth's surface temperature since 1880 to the present. The red line is in a smooth averaging, 5-year average of the annual values, which are shown in the black dots. You can see from this figure that's from about 1960 or so, the planet has been warming in an upward, sort of near constant rate from 1960 to 2018. Before that, there were variations that were actually not related to increased greenhouse gases, but more natural variability. If we look at the spatial pattern of that warming as shown in this figure, you can see that for the most part, everywhere on the planet, the warming has been taking place. It's been taking place at different rates. For example, the darker red values in Europe indicate a stronger warming in 2018 compared to the long-term record. There's an interesting cooling that's occurring just off the southern coast of Greenland, which is related to the melting of Greenland ice sheet water flowing into the North Atlantic and causing the North Atlantic to cool. Most of the energy that's trapped by the greenhouse effect has been deposited in the oceans. Roughly 90% or more of the energy, in fact, has been trapped in the oceans. And this figure shows the increase in ocean heating since the 1960s up to present. And in fact, that heating has been accelerating over the last few decades. If you heat the ocean waters, then you're going to affect the ice that's floating on the oceans at high latitudes. And here is a plot of the extent of North Pole Arctic sea ice during September from 1979 to 2017. As you can see, this downward trend, the melting of the Arctic sea ice year after year over the last 30 or 40 years. It's not just the sea ice that's melting. Of course, the sea ice floats on top of the ice, and when it melts, it has little effect on ocean sea level. But the other thing that's melting are the polar ice sheets over Greenland and Antarctica. And these two figures show the ice mass change in Greenland from 2002 to present, and Antarctica ice mass change from 2002 to present. This is measured by a satellite that's orbiting Earth that can actually detect the mass of these large ice sheets. You can see this very strong decline over this time period due to the planet warming and the melting of the polar ice sheets. And when that ice melts, it flows into the oceans, and thus causing the global mean sea level to change, which is shown in this figure. About half of this increase in global sea level is due to the water that's flowing in from the polar ice caps. The other half is due to the fact that when you warm the oceans, they expand. Warm water expands and thus leads to an increase in sea level. You can also see from this curve that over the last decade or so, the rate at which sea level has been rising is increased. So there's an acceleration of both the heating of the oceans, the melting of the ice caps, and thus an acceleration in sea level. If we look at the spatial distribution of winter warming over the U.S., you can see, first of all, that the warming isn't uniform, that there are certain parts of the country during winter that are warming faster than other parts. Specifically, the Midwest, the upper Midwest, and New England have very significantly strong warming compared to, say, the Pacific Northwest. And so people's perception and reaction to warming is going to vary just based on the fact that they're going to be experiencing warming at different rates around the country. It's important to note that it's not just the average climate that's changing over time, that when you change the average, you also change the extremes of the average that make up the average. And here's an example of that. This is the heavy downpours that have increased from 1958 to 2012 over the various parts of the United States. You can see that in the New England area, 71% increase in heavy downpours versus 27% increase in the U.S. Southeast and 37% in the Midwest. There's very little increase in downpours in the Southwest because the rainfall is minimum there to begin with. The other thing that accompanies warming and drying regions is the increased frequency of forest fires. And of course, when you burn a forest, you emit smoke into the air, leading to an air pollution health hazard. And here are the smoke days per year, the rate at which the smoke in the atmosphere has been increasing over time. And you can see, specifically in Northern California, Oregon, and Idaho, there's been a substantial increase in the amount of days that have air polluted smoke due to the burning of forest fires. The other thing that extreme event that has changed through time is the record number of high versus low temperatures in the U.S. On average, without any sort of change to the climate system, you would expect as many record highs as record lows. And you can see that in the 1950s, that was about the case. There were 52% record highs versus 48% record lows. However, in the last few decades, you can see a significant shift in that. Starting in 2009, the record highs were 56% to 44% record lows. In 2012, it was 90% record highs to 10% record lows. This skewing to more record highs will continue as the planet continues to warm. And there are extreme health hazards related to these excessive heat waves, as evidenced by the event that occurred in France a number of years ago, where over 10,000 people died due to an extreme heat wave event. These changes are also accelerating. Here are just some headlines from the last month of 2018 indicating that the things that we have seen have been observed changing over the last few decades are speeding up. Oceans are taking up more heat. The Arctic ice is melting faster. The Antarctic ice is melting faster. Tremendous acceleration in sea level rise and warming overall. So it's imperative that we begin to focus on this problem and address it before the acceleration gets even larger, which is quite possible in time. So as I noted, the second part of this talk focus with regards to the change in climate system is focused on what's causing the change. And the major cause for the climate change that we've just looked at is due to a change in the greenhouse effect. And a major absorber, a contributor to the atmospheric greenhouse effect, is the amount of carbon dioxide in the atmosphere. We started to directly measure the amount of carbon dioxide in the atmosphere in the late 50s. Charles Kiehl was the scientist who began that effort, and this curve that you see is called the Kiehl curve. There are two features of this curve that you should know. One is the monthly values in red show an up and down cycle. That's the seasonal cycle of carbon dioxide in the atmosphere related to the increase in vegetation in the northern hemisphere summer, which takes up CO2, thus drawing CO2 out of the atmosphere, and then the wintertime release of that carbon dioxide back into the atmosphere. But if you average over time, over the annual cycle, you get the black curve, which shows this secular increase in atmospheric carbon dioxide since the 1950s. It's actually since we've started to burn fossil fuel that the atmospheric carbon dioxide concentration has been increasing. We're now over 400 parts per million, as shown in this curve, which not only shows the more recent atmospheric carbon dioxide concentrations, but using ice cores, we can go back over 800,000 years to look at the concentration of CO2 in the atmosphere. And you can see that the precipitous increase in atmospheric carbon dioxide since the Industrial Revolution really uh, is quite strong relative to the levels of atmospheric CO2 that existed during glacial interglacial cycles over the last 800,000 years. We're now presently well above 400 parts per million. In 2017, it was 408 parts per million. And it's been over 2 million years since the planet had that much carbon dioxide in its atmosphere. Here's a summary that shows the carbon dioxide concentration in yellow versus the temperature curve in red, and you can see this tight correlation between CO2 levels and temperatures, certainly since the mid-1960s to present, with the CO2 levels now above 400 parts per million. This coupling of carbon dioxide and temperature is actually something that's not new. The understanding of it is not new. In the 1850s, an Irish scientist who lived in London carried out experiments to see what gases in the atmosphere were the most effective greenhouse gases, and he determined that carbon dioxide is indeed a very important greenhouse gas. And in 1859, he wrote a paper in which he said, "The bearing of this experiment upon the action of planetary atmospheres is obvious. The atmosphere admits or allows the entrance of solar heat, but checks its exit." That is, the long wave radiation is inhibited from leaving the planet. And the result is a tendency to accumulate heat or energy at the surface of the planet. That is the essence of the greenhouse effect and its effect on temperature. Later in 1896, Svante Arrhenius, a Swedish chemist, published a paper where he asked the question, how much would the planet warm if we doubled the amount of carbon dioxide in the atmosphere? And the value that he came up with was around 5 to 6 degrees centigrade, very close to what we still find with the most modern computer models of the Earth's climate system. Arrhenius also in the early 20th century wrote a book in which he stated that the burning of fossil fuels through the increase of greenhouse gases would warm the planet. So we have known about this effect from a scientific perspective, understanding the physics of it for well over a century. What's the major cause of that increase in carbon dioxide? It is certainly the burning of fossil fuels. Here is a timeline of the world's energy consumption from 1820 to the present. The different colored regions of this plot indicate the sources of the energy consumed, and you can see that coal, oil, and natural gas are the dominant contributors to world energy consumption, or providers of world energy consumption. And it's when you burn those fossil fuels that you emit carbon dioxide into the atmosphere. You might feel that dramatic increase in energy consumption is related solely to population increase, and indeed a significant part of that curve is related to population increase. But if we take that world energy consumption and divide it by the population for every year, we get the world energy per capita consumption, which is this curve, and you can show that you can see that this curve also shows a dramatic increase since the late 19th century, early 20th century, especially over the last few decades. What this indicates that not only are there more people on the planet year after year, but the consumption by people has been increasing. So this is the so-called affluence term. So not only population, but how much a person consumes or their affluence has a tremendous effect on the amount of carbon dioxide in the atmosphere. We can also consider which countries have been contributing most to CO2 emissions. through time. This is from 1751 to 2015. The different colored regions here are the countries, and you can see that presently China is the largest contributor to CO2 emissions. The United States was, up until a few years ago, the largest contributor of CO2. The European Union is also a significant contributor. In fact, if you look at the EU countries, the United States, China, and India, you have accounted for more than half of the emissions of carbon dioxide into the atmosphere. So it's these countries that have contributed, especially historically, more to the greenhouse effect than other countries around the world. In terms of the United States, where does our greenhouse gas sources arise from? You can see that 28% is from transportation, 28% from electricity, 22% from industry, 11% from commercial and residentials, and then 9% from agriculture. So for the most part, a vast majority of the greenhouse gas sources come from transportation and electricity and industry. It is those sources that will need to be modified or mitigated in order to address the U.S. emissions of CO2 into the atmosphere. Up to now, we have focused on the past and how the climate system has changed and how emissions of CO2 have changed the planet. If we want to look into the future, we can't use observations, obviously. We have to use our scientific understanding of how the Earth system works, use the mathematics of that, use supercomputers to solve the mathematics of that problem to simulate Earth's climate system. And the way we do this is we take the fundamental laws of physics, the representation of various physical processes on the planet. Each of those boxes on the left in this figure are what are called grid boxes. They have a certain spatial scale, and we solve mathematical equations for each of those boxes. Those boxes interconnect and communicate with one another. And you do this for the ocean, the atmosphere, the cryosphere, the ice systems of the planet, as well as the land systems. Each component has their own formulations that are all coupled together. Some of the physical processes that you have to deal with in climate modeling are, in particular, cloud processes that need to be parametrically represented, the effects of ocean transport on things like salinity and heat, the flow of fresh water from rivers into the oceans and how that affects salinity. We're looking at a very complex coupled system when you consider modeling the Earth's climate system. The thing that's dramatically changed over the last few decades is the scale to which we can represent these processes. In the 1990s, the typical spatial scale of those grid boxes in a climate model was around 300 miles on a side. By 1996, we were running models that were roughly half that resolution, or 150 miles on a side grid boxes. You can see here in this picture that the shape of Europe and the topography of Europe is becoming more and more well defined as you increase the horizontal resolution within the models. By 2001, the resolution had dropped to 112 miles on a side. Again, you can see the picture showing a more realistic picture of Europe and Greenland. And by 2007, the resolution was now about 68 miles on a side. We're now running climate models with resolutions of about 25 miles on a side, the most current climate models. So the detail, the spatial resolution, the detail, the information that we can generate for societally relevant problems has increased dramatically over the last 2 decades in the field of climate modeling. How well do climate models actually simulate the Earth's climate system? That's a very important question to ask. Climate models have ways of validating or verifying their climate models, and here's just one example. This is that anomaly in global mean surface temperature in degrees centigrade. The black line is the average of all the climate models that were used in the IPCC studies. The various colored lines are different independent measures, observations of Earth's surface temperature. You can first of all see that the observations all agree well with one another, but you can also see that the model agrees well with the observations. Now, the important point about this plot is that dotted line, vertical line at the year 2000, because what was done here was that the models were actually run from the past, actually from 1880 up through the year 2000, with the knowledge of the observed temperature record. So if you were quite skeptical, you could say that, well, the modelers actually knew the target they were shooting for, so they kept adjusting their models to meet the observations. But that's can't be the cause of the agreement for the forecast, which is the years after year 2000. You can see that the models at around the year 2000 were run into the future. We didn't have observations at that time, but the models were run into the future with assumptions about energy use and atmospheric carbon dioxide release, and they projected or predicted a temperature change. Now that we have the observations, we can ask the question, well, how good was that prediction from the models? And you can see the good agreement between the observations and the model indicate that the models actually do a very good job in projecting the global average surface temperature. So this is one way that we can validate how well climate models are doing. So if we take those models and we run them into the future all the way out to 2100, and here's an example of that. On the left-hand side of this plot, you can see the reconstructions of surface temperature back to the year 1000 to the present. Then the black line is the instrumental record. That's the figure that I showed you a few slides back. That's the observed 20th century change in temperature. And then beyond 2000, these are model projections. The red A2 line is the so-called business as usual, where we assume that we continue to consume energy at the rate that we've been consuming it over the past few decades. And you can see that the projected warming for the business as usual scenario is around 4 degrees centigrade, which is quite large compared to anything that we have in the historical record. It's completely out of the range of the historical record. And this slide gives you a sense of how large the warming is relative to the last 1,000 years of the planet's temperature record. In fact, a 4-degree warming is something that you would have to go back millions of years in Earth's history before you saw it, such a warming that occurred. And what's important here is that unlike the past, where the temperature of the planet increased and decreased over hundreds of thousands to millions of years time scale, this temperature change is occurring over less than a century. So the rate of warming is quite dramatic. Just one other projection that you can get from these models is soil moisture, and here's the change in summertime soil moisture at the year 2100. And you can see that there's dramatic reduction in soil moisture in various parts of the world. And specifically, if you look at the US, you can see excessive drying in the Southwest. You can also see excessive drying in Mexico. Very strong drying in the US Midwest, which would be catastrophic for our agricultural systems. So the implications from both of these slides, both temperature and soil moisture, or if we continue to burn fossil fuels at the rate that we have, we're going to see extremely strong changes in the climate system, changes that actually the human species has never experienced in its history. Finally, let me end with what would be required to avoid the worst consequences of that warming. And this curve is CO2 emissions over time from 1980 through into the future. The black curve is the observed CO2 emissions curve from 1980 to present. And the other curves, the yellow, red, and blue curves, are all scenarios that keep the global temperature to 2 degrees warming by 2100. So these are projections of what we would have to do with our emissions scenarios to make sure that the planet doesn't warm more than 2 degrees by the year 2100. And the point here is that if we had started to reduce our emissions back before the year 2000, we could have slowly and gently reduced those emissions over the next 80 or 90 years to meet that target of keeping the temperature less than 2 degrees. But the longer that we've waited, the more we will need to more dramatically reduce our emissions, so that now we're talking about significant reductions in emissions, essentially going from present-day levels to near zero over a very short time period, 20 to 30-year time period, which puts a strong demand on our technologies to actually make that transition off of fossil fuels. So that is a brief summary of what determines the Earth's climate system, how it's been changing over the last 100 years, how we use climate models to look into the future, and what is required for us to avoid the worst consequences of the continued use of burning of fossil fuels. Thank you very much.